to talk about dilations and similarity in the coordinate plane. How can we use dilations to draw similar figures in a coordinate plane? Apply similarity properties in the coordinate plane. Use coordinate proofs to prove figures are similar with some key vocab. How about similar polygons, similar ratio, dilation, and scale factor. Okay, we're going to be working on all that today. Okay, here is what we're talking about, guys. We have been working on what kind of transformations? Rigid transformations, which are what, Mr. Myrick? Which are congruent. We're going to shift. All right, we're going to change into what we now call similar transformations. Big difference. Similar transformations. Okay? If figures are similar, that means they have the same shape. They don't necessarily have the same size. Okay? Right. 1 and 2. Same shape, yes or no? Yes. Same size, yes or no? No. Okay, let's go back to kindergarten here. 1 and 3. Do those have... Oh, thanks for joining us.
You're welcome.
Do those have the same shape? The exact same shape? No, right? One of them's obviously an isosceles triangle, the other one's a right triangle. Okay? Alright, so when we say something is similar, we mean that they have the same properties of similarity, and we will talk about all of that to begin this particular unit. In case you missed Friday, this unit, Unit 2, is the crux of geometry. It is the biggest unit we have in this class. We will be in this unit from now until, I'd say, at least March, probably middle March. Okay, so it's going to take a while for us to get through all this. All right? It's difficult material. I know that. You know that. We'll struggle together and meet each other as little as we can in the process. Okay? Okay, good. Good deal. All right? Move on. Do nothing. What did you do, Miss Booth? All right. Similar polygons. Two polygons are similar polygons if and only if the corresponding angles are congruent and the corresponding side lengths are, oh, here it comes, proportional. All right, guys. When you see the word proportional, you need to think similar. Similar. Proportionality and similar. All right? I want you to make sure you don't have, hey, look, I don't worry so much about the diagrams, all right? I definitely want you to define what similar polygons are and be familiar with these statements. When we say angles are congruent, you'll see this symbol, an equal sign with a squiggly line on top of it. When we say that things are similar, you won't see the equal sign, you'll just see the squiggly line.
What if they're not similar?
Then we don't talk about them. We don't let them in this class. Just similar and congruency. I'll let the other people talk about that.
What other people?
I don't know.
Okay.
There are other people. Jot down what we got here. Okay. All right. Hold on. All right, there we go. All right, similarity ratio is the ratio of the lengths of the corresponding sides of two similar polygons. The similarity ratio of triangle ABC to triangle DEF is 3/6 or 1/2. The similarity ratio of triangle DEF to triangle ABC is 6/3 or 2. I would write down the entire slide, because when I talk about proportional, you'll want to know what I mean. Okay. I'll come back to the slide. Okay, hey. Determine whether these polygons are similar. If so, write the similarity ratio and a similarity statement. I want to know if rectangle ABCD is similar to rectangle EFGH. Okay? Wow, this is what today's classwork is going to look like, okay? Alright, what do you know about rectangles? They're stupid.
One
They're
side
big
is
or
longer than
square?
the other side.
4 sides.
Yeah, and then two of them are congruent.
Mr. McCroskey's talking math to me. Thank you. The opposite sides are what?
Congruent.
So that's 9 and that's 6. What about here?
That's 6 and 4.
Alright, so, hey, check it out. Here's how I would go about writing this similarity ratio. I would compare side AB to side EF. AB over EF. That's one side, right? Then I would compare BC to FG. BC over FG. You see where this is going? I would compare CD. No, I'm not. CD to GH. Right? And then I would compare the bottom sides. DA to AG. DA to HE. Okay? Yes, I said DA.
Why not AB? ABHD?
Because I want to take it A, B, C, D, like this.
I get it.
Okay? Got me?
I don't
Alright.
understand.
Oh my god.
Alright, what is the length of A to B? 6.
Can you move, Mr.
I
Ross?
don't know. The width is.
No, you can move.
Oh.
Move over more. AB is 6. What is the length of E to F? 4. What is the, coincidentally, because I maybe did this before.
9.
What is the length of C to D? What is the length of G to H? Magic. What is the length of BC? 9. What's the length of FG? 6. Now, if you're talking in the back and you did not do well on your test, or, just something happened, yes, that's you. You don't have to raise your hand. Okay? Our whole point about whether or not two shapes are similar means that the sides are proportional. Okay? When I say that the sides are proportional, it means that they have the same ratio, which probably still doesn't mean anything to you. If they have the same ratio, okay, that means that the ratio of one side over another is the same as the ratio of another side over another. All right? In this case, I'm taking the ratio of AB over EF and comparing it to the ratio of BC over FG. Okay? You're going to get confused with this if you aren't already. Here's why. The ratios have to be the same for them to be proportional. In your calculator, what is 6/4, 6 over 4 simplified?
Oh, well.
What is it?
Hang on. 1.5.
1.5. You're right. I don't have 4.5. Okay. Alright, what is 9/6?
You got 3 with it.
Which is 1.5. Pardon me, y'all don't need to be talking, I need to be talking. Okay? True or false? These are the same.
True.
So understand what this means. It means that the side lengths have the same ratio, right? They have the same ratio. They have different fractions. See that? I shouldn't. Is 6/4 and 9/6 the same numbers? No, those are different fractions, right? But different fractions can produce the same ratio. 4 over 8. 2 over 4. Both produce what? 1/2. Thank you. Okay? We could go over and over this, right? You got 3 over 10, 30 over 100. right? See what I'm getting at? 1/3 and 3/9. See that? Okay, guys, all of those have different fractions involved. But when I simplify the fractions, they all give me the same ratio. Okay? So here's what you're doing today. You're taking your base level of fractions, which most of you hate, okay, and we're going up a step, right? We're going to do this over and over again. This is the whole point of this unit, okay? This does not mean that they're congruent, right? I shouldn't have to convince you of this. Is 6 congruent to 4? Okay, then stop right there. Y'all got me? That means that they're not congruent. That's not what we're doing right now, okay? Remember the distance formula? Yes or no? Good, don't have to use it, right? Don't care. They're not going to be congruent, okay? We're going to play this game this time around, right? We're going to play the similarity game and the ratio game over and over and over, okay? All right, if I needed to write a similarity statement, I would say something like this. This is, make sure you get this in your notes. Rectangle ABCD. By the way, if you don't want to write the word rectangle, just draw a rectangle. Okay, you'll see this? This is a similarity statement. I will write it one time. Make sure you get it right. Similarity statement for rectangle. Rectangle ABCD is similar to rectangle EFGH. So I got it right. Rectangle. Okay? So hear me? That is a similarity statement. If you need to do this in your notes, do it. Similarity statement. Right there. Okay? So all you got to write when I ask you for a similarity statement. You'll get better at it. It'll take like 4 seconds instead of 18. Okay? Y'all got me? All right. Let's do a couple more of these. Oh, look, there we go. How would I do this particular problem if I had to do it again? Okay, first off, I would have identify the pairs of congruent angles. I haven't even talked about this because I'm going to talk about it later. Hey, here's the other cool part about similar polygons. The corresponding angles are congruent. Okay, corresponding angles are congruent. All that means is angle A and angle E are congruent. Angle B and angle F are congruent. Angle C and angle G are congruent. Angle D and angle H are congruent. Mr. Hobbs, why didn't you do that here? It's a rectangle. Rectangles have what kind of angles?
90 degrees.
All of them are right angles, okay? So it wasn't a very good example, all right? We just did this. We transferred every single one of these. We converted them not to improper fractions, but to decimals, okay? And wrote our similarity statement. Pretty simple, right? Okay? I'm going to add a little salt to this. Okay? And just like, you know, if this is a wound for you, that means it might hurt a little bit. But if you feel like this is maybe a fine baked potato, it might give it a little bit more flavor. Okay? All right. Dilations, transformation. That changes the size of a figure, but not its shape. The old pre-image and image, they are always similar. Okay? So what kind of transformations do you think we call these? Yeah. Okay. Guys, we call these similar transformations. Right? Yeah. Okay? Okay, good. None of you got it. The scale factor describes how much the figure is enlarged or reduced. All right. Scale factor describes how much the figure is enlarged or reduced. All right? All you need to write down is what I've got underlined or circled. All right? You got me? Don't worry about this just yet because we'll talk about it. Okay? I am going to have you write down this helpful hint because it's rather helpful. Right? If the scale factor of a dilation is greater than 1, it is an enlargement. If the scale factor is less than 1, it is a reduction. Okay? There we go. An enlargement, it increases the size. A reduction does what to it? Decreases it. Here is going to be what trips you up, yo. Okay? When you have a dilation, your dilation must be between 0 and 1. Somewhere in between there is going to get you a reduction. Anything bigger than 1 gets you E-N-L-A-R-G-E. Something enlarged. Right? Notice what numbers we're not going to deal with.
Negative.
We don't deal with negative numbers. Okay? You got me? So if you come to me and you're like, Mr. Hobbs, I don't get it. I wanted to make it smaller by a half, and I multiplied by -2. If you want to get something smaller. Okay? What happens if I multiply it by a scale factor of 1?
It's gonna be the same.
Same size. Now, here's the kicker. Okay? If I have a shape, and the shape stays the same, and the size stays the same, what is it?
Congruent.
Beautiful. Hard. Okay. Yeah. So if we have a scale factor of 1, we're talking about congruent transformations. Oh, Mr. Hobbs, it makes so much sense now. Good. Okay. All right. That's not going to happen. Okay. I won't trick you with that one. All right. I just want you to, if you get the fact that that's what congruent means, we're in good shape coming out of last unit, right? So if I had said last unit, apply a scale factor of 1 to every single transformation, you would have been doing it right. Okay. All right. See what this might look like in a actual problem. Yeah, it is. Don't worry about it. All right. Here we go. It says draw. Ooh, okay. Draw the border of the photo after a dilation to a scale factor of 5 halves. If I have a scale factor of 5 halves, hey guys, I will take each coordinate point 0, 0, right? 0, 4, 3, 4, 3, 0. Individually multiply each of those coordinate points by 5 over 2. Mr. Hobbs, I ain't got to do it when it's at 0, 0, because anything times 0, 0. Oh, beautiful. Good. Okay? You're right. You don't. Okay? But you do have to multiply 4 times 5 halves. You get 10. 3 times 5 halves, 7.5. 4 times 5 halves, still 10. 3 times 5 halves, still 7.5. Okay? Right? Each coordinate point gets multiplied by the scale factor. That's simple. That's dilations. That's all it is. Okay? It hopefully will click in about 2 days. Alright? I'm serious in saying that. Hopefully in about 2 days of doing this, you don't even have to worry about it. It's the simplest thing we'll do. Yo.
Like while you're doing that, like, can you not just do like C? Because if you multiply C by it and if A stays the same, it's a rectangle. So to the side, you can put another term through it. So you just did C, you could draw a rectangle.
You could, McCroskey. I would not fault you for doing that. What he's saying is that the coordinate points of C are the only thing that you're having to multiply everything by. So you could take your little shortcut and be on your merry way. All right? But it ain't always going to be like that. Okay? Sometimes I'll have to do this to you. All right? Draw the coordinate points 0, 0, 0, 10, 7.5, 10, and 7.50. Right? And then by different ones. All right? Let's see if y'all can do this one on your own, right? Write this one down. First off, know this, that's 4. Okay, this is 1, 2, 3. Alright, take just a couple minutes, read the directions, plot your points, see what you can come up with.
Smaller rectangles.
Yeah. Yeah, what's our process involved here?
Multiply everything times 0.5.
Multiply everything times 0.5. Multiply everything times 1/2, right? First off, before I even do that, listen up. Plot your points. Well, when you hear plot your points, that means write on a graph. Take the plotted points and give them coordinate values. 0, 0, 0, 4, 3, 4, 3, 0. Guys, if you didn't get that step right there, you're going to be lost today, right? You got me? Okay? Now, Mr. Hawks, I can just see it and know what to do with all of it. Okay, that's fine. I like things more organized, all right? But understand, what's our end result here? If I multiply each of those coordinate points times 1/2, which is the same as 5, okay, then I would get this end result. 0, 0, 0, 2, 1/2, 2, 1/2, 0. Right? I heard this already, but did that go bigger or smaller? Okay, so what do we call, understand something, right? I don't want you to get used to saying bigger or smaller. What do you think I want to get?
Reduction.
I want you to get used to saying enlargement or reduction. Okay? Enlargement or reduction. Alright? Everybody with me? Okay, then I would go back and plot those points. Alright? Now I got this one. Given that triangle TUO is similar to triangle RSO, find the coordinates of U and the scale factor. Alright? Guys, look at what happens here. Okay? Look at what happens here. If they are similar, that means that the sides are proportional. Okay? I know this is negative 12, 0. Okay? But how far is that from 0, 0? We call that absolute value. Right? No, it's good. Okay? In a coordinate plane, that's at negative 12, 0. I ain't got a problem with that. Okay? But when I put that into a proportion, I don't want to put negative 12, right? I don't want to put negative 12. I want to put 12 over 9, okay, equals 16 over x. So let's say I had x right there. What would I do? I think y'all seen this before. Yeah, how do I solve for x? Cross multiply, right? You got me? I'm going to cross multiply. 12 times x, 16 times 9, 12x equals 144. Divide both sides by 12. That means that OU is 12. Okay? The coordinate point would be 0, 12. Okay? Alright. Utilize on the y-axis, so its x-coordinate 0. Since OU is 12, its y-coordinate must be 12. Coordinates of U are 0, 12. Scale factor is 3/4. What? Okay. How did they go from 0, 16 to 0, 12? They applied a scale factor of 3/4. Mr. Hobbs, how could I get that? Divide 12 by 16. Divide 9 by 12. That's how you get it. Okay? Those are the problems that we're moving towards. I don't know if we'll get there today. Y'all hear me? Okay? So it's not like, so if you can't do this by the end of the day today, don't freak out on me, because we're going to do this again tomorrow. All right? So don't freak out. Just understand, that's what we're getting towards. That's kind of the end goal that we want to get out of this week and this unit. Okay? Any questions on that? Good deal. Classwork number 7 is what we've got for today.